folks, welcome back. This is Savannah and you're watching Toto Physics. Now let's begin Chapter 2, Motion in One Dimension. Previously, we learned that physics is the study of physical processes. And one thing that all physical processes have in common is that they involve motion. Motion really is everywhere. Take you, for example. Looking good there? You probably move. And not only can you generically move, you can chase things like your cat, and your cat's running away, but then becomes distracted by an insatiable itch, and scratching that itch launches a projectile flea, which lands splat on that rock. Now, it might look to you like that rock isn't moving, but actually it is, because the rock is on the Earth, and the Earth is rotating at almost 1,000 miles per hour. And even if we launch that rock into space, and neglecting the fact that the universe is expanding, it could somehow be held relatively motionless. If we just zoom in on that rock, and zoom in more and more, we'd see that the very atoms that hold the rock in place are actually dancing to some minute wiggle of a dance as they sit snugly in their molecular lattice. So yeah, there's a lot of motion going on, and it can get complicated, but let's start with the basics. You may be used to hearing the word mechanics referring to fixing cars or the like, but actually, in physics, mechanics is the study of motion. Now we can break mechanics into two subfields, kinematics and dynamics. Kinematics comes from the root word kinemat, meaning motion in Greek. This may remind you of a familiar word, cinema, which shares the same root but refers to movies, or as the old folks called them, moving pictures. Kinematics is how we describe motion. Now, I don't mean describe like with words such as fast or slow. What we mean here is using math to model the motion that we observe in our everyday lives. Dynamics, on the other hand, refers to the study of the causes of motion, namely forces, which we'll study later in this course. But for now, let's focus on what's necessary for describing motion. We can describe an object's motion mathematically by considering a few measurable quantities, which will be discussed throughout the chapter. We'll introduce position, where something is, displacement and distance, related to how far something is moved, velocity, how it's moving, and acceleration, which is how that motion is changing. However, measuring any of these quantities will depend on defining our reference frame. A reference frame establishes a point or state of reference from which to measure positions and relative motions. Geometrically, this means first establishing an origin, or 0 point. From this point, you can extend a set of axes defining both a positive and negative direction for motion in each dimension. For one-dimensional motion, we just draw a line. Here, you can observe motion back and forth. For two-dimensional motion, we use the xy coordinate plane, where these two axes can be used to distinguish motion back and forth or up and down. For 3 dimensions, we use 3 axes, which represent the back and forth, up and down directions, as well as into and out of the screen. As you may guess from the title of this chapter, we'll be sticking to motion in one dimension. Now we have one final caveat to address, which is that how an object's mass is distributed can affect its motion. It's relatively easy to characterize motion for small objects like this little blueberry, where all the mass is distributed quite evenly in its tiny volume. But consider these 2 eggs. One of these eggs is raw, while the other is hard-boiled. Look at what happens when we spin them. Although we're looking at the same object, they move in different ways when subject to the same stimulus. And one does something quite unexpected. Can you guess which egg is which? All of this egg business boils down to this. In order for us to simplify our calculations, we'll treat all objects, eggs, blueberries, cows, and people, as point-like or particle-like objects. This means that the object has no volume or size other than a single point, and that all of its mass will be concentrated at this point. You'll see later in the course why this is often a pretty good approximation.